Hello dear friends and welcome to another electronics tutorial. Today we're going to be discussing transistors. So transistors are the building blocks of modern electronics. You can find them in any integrated circuit, in most of the household items from washing machines to uh, refrigerators to any component that has an electrical switch. Mainly, their function is to amplify a voltage or a current by a amplification factor called beta or HFE. In this small example, you have, for example, a microphone input signal, which is very small, about 40 millivolts, 40 microvolts, which is then, let's say we take the signal, we want to output this in a speaker so that we can hear the person speaking in the microphone. For this, we can use a transistor. And for example, if we take a beta of 300, then we will amplify this 50 micro volts signal level by 300, and then we'll get like a 15 volt output swing for the speaker. So this would be a amplification of about 300 to this quite small microphone signal. Regarding the types of transistors, there are two types: bipolar junction transistors and field effect transistors. The main difference is the bipolar junction transistors amplify current, and the field effect transistors amplify voltage. So the amplification here differs from one type to another. As a general structure for the transistor, the bipolar junction transistors have a base, which is the command signal. They have a collector and an emitter. So how does this transistor work? For this case, where we have an NPN transistor, we inject current into the base to the emitter, and this will cause the current to flow from the collector to the emitter. So we insert a very small base current, and the collector to emitter current will be amplified by this factor. So for example, we insert here 10 10 microamps. We amplify this by 300, and then you will have here 30 milliamps going from the collector to the emitter here. In case for the PNP transistors, also bipolar junction transistor, um, the arrow is from the emitter to the base. So basically, the arrow indicates from which the current should be flowing so that the transistor will open. For the NPN, it has to flow from the base to the emitter. For the PNP, it has to flow from the emitter to the base. And in this case, if there is a current flowing from the emitter to the base, it will allow current to flow from the emitter to the collector, but amplified by 300. So if you have um, a 10 microamp current from the emitter to the base, then you will have 30 milliamps from the emitter to the collector. Regarding the JFET transistors, so the JFET transistors are a bit different from the MOS transistor, metal oxide semiconductor, because they have a constant current, a very small current flowing from the drain to the source. So this means that from the gate to the source, they can measure very high impedance here, because they would always measure the voltage level here between the gate and the source. The JFET transistors are usually used in some of the best um high impedance applications. So let me give you an example for EKG signals, which are connected to the body. Usually they are used for high precision amplifiers. The JFET transistors are used for instrumentation amplifiers. So very high precision equipment uses JFET transistors as an input type of transistor. For the MOS, metal oxide semiconductors, these work when you have a voltage between the gate and the source. They will open the drain source connection here, and will allow current to flow from the drain to the source. So they act as a switch. So you have a voltage here. This will allow a current to flow here from the drain to the source. Same for the pMOS. So for the pMOS, you need to have a voltage from the source to the gate. So when you have this voltage here, usually if most transistors are power transistors, so here you would need kind of a considerable voltage. They are turned on. So for a bipolar junction transistor, this can open at 0.7 volts between the base and the emitter. For a MOS transistor, you would need about 5 volts, some open even at 10 volts. So you need a much higher voltage here, but they are much faster than standard bipolar transistors. One thing I consider to be quite important to understand a bit the functionality of a transistor is their internal structure, how they are internally designed, what is under the hood of a transistor. So here are the bipolar junction transistors and their structure. As you can see, they are PNP and NPN. This means that here you can see the substrate for each of the transistors. And we know from the diode video that a diode conducts from a P to an N substrate. So these here can be considered diodes for the bipolar junction transistor. They even in real life they have about 0.7 volts, very similar to a diode's voltage drop. Some have even smaller, depending on how large one of these layers is. So basically, here you have a diode. When this diode conducts, this means that the P connection would be connected to the other P layer here and will conduct current in this direction. In case of NPN transistor, if you have a base emitter, so from here, because the first has to be a P substrate. So if you have a current going from the base to the emitter, this will connect the two N layers, and here you would conduct current. Going forward a bit, because here you can see that these are current driven, so they are diodes. For a MOS transistor, you have you have here a channel that is formed between the gate and the source. So what happens when you supply the gate with a voltage? So you have a voltage between the gate and the source. Here you create a channel under the gate between the drain and the source, and this channel here allows current to flow from the drain to the source. If there is no voltage between the gate and the source, the channel is destroyed, or it's not working, so then you would not have any current going from the drain to the source. The fact that this is acting as a capacitor here is one of the main reasons why MOSFET transistors can switch so fast. So most transistors, you would see them in all power electronics application where you need very high switching time. Most of the power supplies that I design are using most transistors. A bit going forward, that we look a bit how they are looking in real life. So here it's a bipolar junction transistor. It's quite similar to a JFET transistor, three terminals, base collector emitter, gate drain source, and here is a MOSFET transistor. Uh, the um, the MOSFET transistors here are also having a cooling plate here. This is usually connected to the part that is dissipating the most current. So in the case the most heat, in the most cases of nMOS, the drain is the point where it's the hottest, and in the pMOS MOSFET is the source. So be very careful when you are putting two MOS transistors together, because if if they are connected through a radiator here, then you would be connecting the drain with the source of the other one, and you may create accidental short circuits. So always measure for a MOS transistor, always measure to make sure that you don't accidentally short circuit the cooling pad for the transistor to a voltage level so that you don't nothing explodes. Okay, going forward, here I've taken one of the most common transistors, a BC817, and here are some of the parameters for this transistor. So the collector first of all, this is a NPN transistor, bipolar junction. The collector emitter voltage is 45 volts. I would not go that high with this transistor. I would kind of use it maximum for 30 volts. The emitter base voltage, so this is in case it's polarized between the emitter and the base, has a maximum of 5 volts. Um, then it will do structural damage to the transistor. Some continuous current, so the continuous current that can go from the collector to the emitter for this transistor, it's about 500 milliamps. The power dissipation, which is very, very important that we don't through the calculation. So the power is voltage times current. If this is the current, we can at max current we need to calculate so that the transistor doesn't have more than a voltage that would exceed this power dissipation capability. And also please take into consideration to always leave 20% of this total power in reserve so that the component is not damaged and you're not working at the very edge of the functionality or the specification for the component. Another very um, important parameter is the collector emitter saturation voltage. So this is the voltage where you've turned the transistor on, and it's the voltage between the collector and emitter. How much is the resistance between these two components? And it's a voltage drop of 700 millivolts here. This is for 500 milliamps and 50 milliamp base current. So it's quite okay collector emitter saturation. And the base emitter turn-on voltage. So this is the voltage when we actually switch the component on. How much do we need between the base and the emitter to turn this component on? And here we have the maximum value. It's 1.2 volts. So at the 1.2 volts, we're fairly sure that this component is fully switched on. Going forward, some of the basic parameters regarding the amplification. So as we've discussed, beta or HFE it varies quite large. This is why usually you don't the transistor doesn't have this high amplification. So usually for an audio amplifier, for example, you have multiple stages, but without without uh, a feedback network, this transistor can go to 600 times the input current. So this is quite quite high, quite high amplification factor. But there are usually this goes from about 100 to 600 for this component. For 100 milliamps, I think this would be the most that you would be able to get from this component, 600 times the input current. Regarding some of the main topologies, so the first and basic topology for a transistor is the switch, the on-off switch. So in this case, here we have a transistor and an LED, most basic electronic circuit. You put here 5 volts, which means the transistor is turning on through this 1 kilo ohm resistor, and this means that the LED will light. When here you have 0, this means that this transistor would have no voltage between the base and the emitter, and this would then turn off the LED. And here is the equivalent circuit. So the equivalent circuit is this transistor is transformed into a switch, which is driven by the voltage that we're giving here. Another very important part of applications for transistors is a simple audio amplifier. So in this case, the transistor, in the previous case with the switch, the transistor worked with the very high amplification. So it took the current going into the base and then did a times 600 amplification, and then this would act as going from no current passing through here to the maximum current that can pass through here. With an amplifier, it's totally different. You are working to amplify the value here on the input. This is a very simple circuit in which you have a signal from a microphone. This signal will travel through this capacitor here. As we discussed in the capacitor video, the capacitor when supply the signal, it's a short or conducts the signal from one side to another. This then goes to a bipolar transistor, and then this bipolar transistor drives the speaker here. Very important to note that driving the speaker, you don't need to have a DC component, otherwise you would break the speaker here. So we use a isolation capacitor here for the supply. This is quite simple circuit. You can use a 9 volt battery to supply the whole circuit here, and it would amplify the input signal to provide the correct output. And this is another circuit. It's even simpler than the previous one. So here there is a 9 volt battery, there is a speaker, and here it's a 13007 transistor or a TIP 31 transistor. The circuit will take the value from the jack. Unfortunately, you can see here the jack is using only one signal, so it will be only the left signal. The right signal is in air because for the stereo signal you would need the two signal values. So it's going to take one audio input. It will pass through this capacitor here and then go into the transistor, which is then going to drive the speaker. And the transistor will use the amplification because these are power amplifiers, power transistors. They would have a much smaller beta. So they typically have 40, 50 times the input voltage level. So here would not be a problem to saturate the speaker through the signal. And the last and one of the most used functions for the transistor is voltage regulator. So as we discussed in the previously, between the base and the emitter of a transistor, there is a diode. It's a PN junction. In this case here with the voltage regulator, here you have a unregulated voltage. You may have like 12 volts, 20 volts, different voltage levels. On the output here, you will have only two voltage drops. So the output would be stable. You would have one voltage drop between on the Zener diode, more about the Zener diode in my diode video, and one voltage drop between the base and the emitter. So this means that you would have always on the output, you would have the voltage between the base and the emitter minus what is on the Zener diode minus the base emitter voltage. So here you would need, for example, if you take a Zener of 8 volts and you have a base emitter voltage of 1 volt, then you will have 7 volts on the output. We will discuss this a bit more in detail in the simulation part, where we can create a couple of voltage regulators, and it would be a quite interesting challenge to create different voltage levels. And it's just repeating the circuit and understanding if you need a 1.8 voltage level for the circuit, you can create one with a transistor, a resistor, and a Zener diode. And it's that easy. One thing you have to take into consideration is the power dissipation for this transistor here, because yeah, as we've discussed here, the transistor has about 330 milliwatt power, so the voltage drop on between the collector and emitter times the current going through the transistor should be smaller than this. So be very careful when designing voltage regulators, because this type of linear regulator, because these are linear regulators, they tend to have yeah, they tend to have quite bad dissipation on this component. Okay, great. Let us go forward and get to the simulation. Okay, so now let's create a new circuit in TinkerCad, and for the TinkerCad we've used the software for most of the tutorials till now, so you could go into the resistor tutorial where I discuss a bit more about the tool. Let us first select all components, and let's search for a transistor. So going down in the list, here is a NPN transistor. Okay, you can see here it has the collector, the base, and the emitter. So the first circuit that we're going to discuss now is the switch, where we should be able to switch this transistor on and off from no load to maximum load. So let me rotate a bit this component with the R key on the keyboard, and let's take a power supply, just that we supplied the circuit. Okay, and then let us take a LED, a resistor here and a LED. So the LED we supply from anode to cathode. So I'm going to rotate this anode to cathode, and let's connect the resistor with the LED and with the transistor together. So what we want to do is to light the LED and turn it on. Okay, so now we have connected the collector for the LED, and now we are going to put the emitter at the negative voltage. Okay, just let me style this up a bit. Okay, the next step is to give a command to this transistor. So the transistor is set in a switch between the collector and to create a switch between the collector and the emitter of the transistor. And now we just need the command signal. So for the command signal, we are going to take a resistor and place it in the base of the transistor so that we limit the current to the base of this transistor, that we don't break it. So like driving a voltage higher than 1.2 volts between the base and emitter will break this component. And let's get um, a function generator here so that um, we can supply this with a PWM signal, pulse width modulation. It's a rectangular signal. You can see it here. This is the PWM signal. One quick setup for the signal generator. So for the frequency, just that we see it, let's put 2 Hertz. For the amplitude, 5 volts is more than enough, and the DC offset is 2.5. So what would this give us? They would give us a signal going from 0 to 5 volts with a 2 hertz period. I mean, this would be the period. 1 hertz is once a second, 2 hertz is twice a second. And um, the offset is the value, the reference value from which the amplitude is calculated. So the amplitude is 5 volts. So if we split it in two, we have going up 2.5 volts and then going down 2.5 volts. Okay, let us then connect the positive line from the signal generator and check again frequency 2. The supply we have to increase a bit, just that we have a bit more voltage driving here. And for the resistor, let's put a smaller value here, let's say about 400 ohms. Yeah, it would be enough. And here it's 1 kilo, it's more than enough. Okay, let's start the simulation and see if this LED turns on and off. And now we can see that the LED turns on and off according to the driving pulse from the signal generator. We can reduce the frequency here. This is once a second, and then or we can increase it to 5 to 5. So it's 5 hertz. It's turning on and off quite fast. And but let's bring this down to 2 hertz so that we can see it turn on and off. Great. So this is the transistor working as a switch. We are just giving a command signal here to this resistor in the base when we want this LED to turn on and off. Okay, great. The second part of the simulation is related to a to the amplification of a bipolar transistor. So I just Control A and Control C everything, and then Control V, so that I would copy the design again. First of all, let us look a bit how this component would work in an amplification mode, in an amplifier mode. So let me delete the signal generator and let us take a power supply here. So let us connect a power supply to the transistor, just that we see a bit what is the beta for this transistor. Maybe it's 100, maybe it's 50. How much is this transistor actually amplifying here? So let us connect the supply, and let's start with a voltage of 1 volt. Let's see what is the um, output current, or the current drawn from this power supply, if we're supplying this at 1 volt. Okay, so we can observe now that we are supplying 1 volt to this transistor, and this transistor is pulling 284 microamps and has an collector emitter current of 24.8 milliamps. So let us do a small calculation. So 24.8 milliamps divided by 0.284 microamps, the component at the moment has an amplification of 87.3. Okay, so this means that the transistor is amplifying any signal from the input, any current coming from the input, by 87.3 times. Okay, great. Let us do the same calculation, but let's say we give it an input voltage of 2. So this means for 2, I think we are already into the saturation of the transistor. So we have 24.9 divided by 1.28. So this is 19.45. This means that the transistor is saturated, so it cannot amplify the current even more than it is already amplified. Okay, great. So this means that we should not reach this 2 volt input voltage. Let's start to create our amplifier circuit. So we are going to need a power supply. We are going to need the transistor. We are going to need a load. We can even place this load in the audio range, which is a 8 ohm speaker. We assume this is an 8 ohm speaker here. Let us take a signal generator, and let us take a base resistor here. Okay, let's connect everything together. So from the collector we go to the resistor and the power supply. To the base we we connect the driving voltage from the power supply, okay, from the positive line. Okay, and from the negative input from the power supply, we connect to the emitter, and the negative from the other supply, we connect also to the emitter. So we have the same reference voltage level, which is negative from the signal generator, negative from the power supply. Great. One last thing we need is to see the signal. We want to see, okay, we are feeding this transistor a signal. Let us see how the signal is looking. For this, we're going to use an oscilloscope, and let us connect the negative to one side of the speaker and the positive to the other side of the speaker. Great. The power supply is, maybe we can put even more, let's say 15 volts. Power supply, we have a 8 ohm resistance here, and let's put here, we need a bigger resistance for the base. Let's put a 10 kilo ohm resistor for the base. Regarding the input signal, let us go with the sine, because audio signal is looking like a sine signal. Frequency, the audio signals are between about 200 hertz and 4 kilohertz usually, but they can exceed this limit. Let's put how many hertz? We can leave it at 2 hertz. It doesn't matter. Where we have to work is the DC offset. So for the DC offset, let's say we put 1.5 volts, and amplitude we put 1 volt. So this means that we will have here 1.5 volts, and then above and below this 1.5 volts we are going to have the signal, the sine signal. Let us start the simulation, and here we see a beautiful sine signal. Now what we are seeing now is on a 1 volt line, which means that the signal here, this is 1 volt, so this is very, very low voltage level. So let me check a bit here. It's a sine wave, 1 volt amplitude, 1.5 volt offset. From the power supply, it's draining a lot of current. Let me maybe increase this to, yes, so it's doing an amplification here. If we increase the load a bit so that we can clearly see the signal, you can see that the signal is going from, here are 20 volts, so from top to bottom, and here are 10 volts from one side to another. So we have the signal, our signal has two, four, it has 2, 4, 5 and something, so it has about 5 volts input, and we derived a 1 volt 5 volt output, and we've inputted about 1 volt. Now of course we can play with the audio amplifier even more, but this would be a bit more discussed in the audio amplifier tutorial, where we are going to discuss in the first instance one stage of audio amplifiers, and then we're going to do several stages, a 3-stage audio amplifier, which is becoming a bit more real design here. Okay, let's stop the simulation. So here we have amplified times 5 an input voltage. The last part, and the last the application for the transistor is the one for a voltage regulator. So this is one of the most common circuits used in electronics. We're going to take a transistor, we're going to take a Zener diode, and we're going to take a resistor. The transistor, where we can create rotate it. So we need the collector on this side, the base here to the reference, and here we have a Zener diode which is a 5.1 volt Zener diode. Great. Let us set the power supply. The power supply is at 15 volts, so this is okay. Let us connect the components. So the ground goes to the anode of the diode because it's a Zener diode. This we connect the diode to the base of the transistor. We then connect the one terminal of the resistor, which is a 1 kilo resistor. It's quite okay, to the Zener and to the collector here. And then let us put an output here. Let's say we want a 100, or yeah, we can put 100 ohm output, stable value. So stable output. Okay. And I just have to connect these two wires again. Okay, a bit of styling. And the supply goes into the collector of the transistor. Let me style this a bit again. It goes beautifully in the input. And now let's see how the output value looks. So we take a multimeter and we connect this multimeter to the output resistor. So negative here and positive here. What are we aiming with the circuit? We need a 5 volt output. So let's start the simulation, and we have a 15 volt supply and a 5 volt output. Okay, but let's say we want a 7 volt output. Then we just put a 7 volt Zener, and then we have a 7 volt. But what about a 3.3 voltage output? Because the 3.3 is quite common for some controllers that have a 3.3 volt supply. Then we put here a 3.4 volt Zener diode, and then we get a different voltage level. Okay, this is really interesting, but what here, let me put 5.1. But how would this circuit actually work in case of an active load? An active load means that we're using, for example, switching some LEDs, uh, where you sometimes have 58.9 milliamps, or you sometimes have 100 milliamps. So let us add a LED and a button, because we need to switch the LED on and off. Let me rotate the anode to be on the top side. For the LED we need a resistor, because these are quite let me put here a 100 ohm resistor. Okay, and let us connect this circuit, this to the rest of the circuit. So we're just pushing everything back to the anode of the Zener diode, and then we're connecting this terminal to the output so that we can switch the load. Okay, let us start the simulation. So we have 58.9, and now we press the button and we have 86.9. Oh, and we get an error. I think that the resistor here is still too small. Let us put 200 ohm. 200 ohm, and now you can see active load 20 milliamps, and there is the voltage level drops by 1 millivolt. So 1 millivolt, it's insignificant. You have almost a constant voltage, but even more, we can add a reactive load. So let's take ourselves a DC motor, Here we have a DC motor. We are going to connect the first terminal to the resistor here, and then the second terminal to the cathode. So we make sure that we have current flowing through this in parallel with the resistor and the LED. And let's start. So 58.9 milliamps, 0 RPM on the motor, 0 current through the LED. We press this 150 milliamps, 152 milliamps. The motor is switching, the LED is turned on. Voltage drop between pushing the button and between having 152 milliamps and 58.9, so this is a 100 milliamp load. The voltage drop here for 100 milliamps is 40 millivolts, so it's insignificant. So this is a very, very good voltage regulator circuit. I recommend you use it quite often when you need a voltage reference or um, a voltage level. It's simple to make. It's quite efficient to regarding the number of components, and yeah, you can create your power supply quite fast and easy. With this being said, this was the last circuit for this tutorial. If there's any other circuits that you are interested in me for me to review or discuss or design together, please write me down in the comments. I would like to thank you for your time and wish everybody a great day.